Okay folks, so in this video the objective is the title. We want you to know your library of functions, as it's often called. This is a collection of functions that we want you to know so well that you ought to have them just flat out memorized. In math I try to memorize as little as possible, but these are the building block functions from which so much else is built that it is absolutely essential to have these functions memorized. My recommendation would be to put the name of the function on a flashcard, and on the back side of that flashcard put the graph of it. And then rehearse those until you have all of them memorized. So I want to show you, this is kind of my own wording here. What I like to do when I'm given one of these functions is I want to make sure I can do a quick rough sketch of the graph, and then also when necessary do a careful sketch. And I want to point out that I have the rough sketch memorized. If somebody asks me to graph the function f of x equals x, I know that its graph looks like this. There's the graph of that function, f of x equals x. By the way, this is called the identity function. So if you hear that name identity, that's what we're referring to in this context. And notice I was able to sketch this function without plotting any points. Of course, I could always go build a table of values to plot points carefully, but I want to point out that I had the graph memorized. I only do this if I want to label some points. So for example, if you were to plug 2 into this function, you would get f of 2, which is just 2, and we've got the ordered pair 2, 2. Likewise, if we were to plug negative 3 into this function, f of negative 3 is equal to negative 3. And in fact, you might be seeing why math people call this the identity function. If I put a couple more points on here, just to ease the sketching of it, you might see why people call this the identity function, and that is it simply spits out whatever it is you plug into it. That's why it's called that identity function. Now we want to be able to talk about the domain and range of this graph. So we see that the domain is any real number. I won't do this for all of these graphs, but if you were to take this graph and you were to smash it onto the domain axis x, you would see that its domain here is all real numbers. That's what we have. Likewise, if you were to take this graph and you were to, the fancy word instead of smash is the fancy word we use is project this graph onto the f-axis or the f of x axis or just the y-axis, if you were to project it onto there, there's the range of that function, and so the range is also minus infinity to infinity. I want to say a few other things about this function. This function is increasing on minus infinity to infinity. That is, as you go from left to right, the graph rises. That's what it means to be an increasing function. And it's increasing everywhere on its domain. The other thing I want to say is that f of x is an odd function. Notice that when we plugged in 2 into this function, it spat out 2. When we plugged in the opposite of 2, if I plug in negative 2 into this function, it spits out negative 2. So we see here that when I plug in opposite inputs, I get out opposite outputs. That's what it means to be an odd function, and odd functions have this property that they are symmetric about the origin. Meaning if I took a point and reflected it over, there's the origin right here. If I took this point and reflected it over the origin, I land right back on top of the graph of this function. So folks, I'm going to do the rest of these for you on this page. But I actually encourage you to pause the video and try to do each one of these before I do. So let's have you pause the video, try to do number 2. So let's look at the graph of the x squared function. So again, this is where I'm hoping that you're able to do a quick rough sketch of this without needing to plot any points. And so again, I just have that graph memorized, but if I want to be careful and I want to plot points, I can. For example, if we take in 1, this function outputs 1. If we plug in 0, this outputs 0. Ooh, that looks like the identity function, but no, if we plug in 2, f of 2 is equal to 2 squared, or 4. So we could go ahead and carefully plot a few points on the graph of this function. So So if we plug in 3, it spits out 9. If I plug in -3, it also spits out 9. That's interesting. And let me just plot a couple more there. And here I can now sketch the graph of this function. You'll notice that when I sketched it with these scaled values, it looks a little bit different than when I did my rough sketch. That's just a sort of an artistic thing that math people do. We like to kind of emphasize that parabolic shape. It's a matter of scaling and perspective there. Okay. So this is our f of x equals x squared function. Its domain is from -infinity to infinity. Why is that? Because I can take any number I wish and I can square it. That's not a problematic operation. Its range, interestingly, is not all real numbers. The squaring function can only output positive numbers or the number 0, because 0 squared is 0. So the range here, if you were to project this onto the y-axis, the range is from 0 to infinity. Notice that this function is decreasing for numbers between -infinity and 0. That, when I say decreasing, I mean as you go to the left, the functional values are decreasing. Let's not draw that arrow there. So this is decreasing. And it's increasing. What do we mean by increasing? Well, as we go to the right, are we going up? That's what we're asking here for increasing. And it's increasing on 0 to infinity as we go to the right. Notice that we don't say that it's increasing or decreasing at the value 0. This graph is symmetric about the y-axis, and that's a hallmark of being an even function. What do we mean by an even function? Well, notice when we plugged 3 into this function, it outputted 9. I'm now going to plug the opposite of 3 into this function, and it also spits out the output of 9. So opposite domain values, in this case, gave the same range value. That's the hallmark of an even function. Even functions are symmetric about the x-axis. We could say more. We could say that f has a local minimum at the ordered pair 0, 0. So folks, again, what I'd like you to do is pause the video and try to do as much of this as you can about the cube function, and then I'll join you in a second. So here's the graph of our x cubed function. It looks something like this. I want to point out here, especially since this is, if this is for a pre-calc class, we've learned about the graph of the tangent function. This is not one period of the tangent function. This graph, it's worth noting, has no asymptotes. You might say, well, Charles, it looks like this has asymptotes. Well, that's not true, and you can see that because notice that this function, the x cubed function, is defined for all real numbers. And for any number we plug in, it's possible to cube it. And so we don't have that asymptotic behavior that you might see when you have functions with restrictions in their domain, simple functions with restrictions in their domain. I didn't ask you to fill anything in here. We'll just go through and check the boxes. We'll notice that the domain is all real numbers, the range is all real numbers. This function is always increasing. Always as I go to the left, the function gets higher. That's an interesting question. Notice that it is, the increasing interval does include 0 there. This is an odd function. So for example, let's plot some points here. If I were to plug in 2 into this function, it's going to spit out 8. And if I were to plug in the opposite of 2, it's going to spit out the opposite of 8, so -2, -8. That, when you plug in opposite numbers, you get out opposite outputs, is the hallmark of an odd function. And then here's just a quick rough sketch, I guess, but placing some points on here. So again, folks, my goal is twofold. One, that you can quickly sketch the graph of the cube function without needing to plot any points, or maybe just the origin, without really need to plot anything at all. But when necessary, you can go through and you can quickly and carefully label some points on the graph of this function. So this is our x cubed function. All right, folks, I'll see you in the next video where we'll pick this up.